Welcome back, everybody. And before we begin, I just wanted to give you a kind of bird's view of what we will be doing today. And as we've seen during the lab sessions, we are getting close to the deadline. And one of the things we wanted to do this week was actually to try to write an introduction, an abstract, and set up the list of references for the report. Typically, the kind of abstract and introduction you end up writing is something you would probably modify when you write the final report. Because at least if I look at myself, I normally write the introduction and the abstract when I'm really done with everything. But this is more to get you guys started, and we will try to give you some feedback on what you've written. Next week, we will not have any weekly exercises because that is the week when probably most of you will be pretty busy with wrapping up everything. So the topic today is something which we will also continue with next week. And this is something which we said lies at the heart of machine learning. And we are going to look at optimization methods. We are going to look at the standard gradient descent. We will look at other methods for actually minimizing these functions. And as we saw last week, when we started to look at logistic regression, which is a classification method, and it's one of the simplest possible ones, where we replace the function f of x, which we had in regression, with a probability, p of x, and then we made a model for that probability. Then we ended up with a set of equations which would be non-linear in the parameters beta. And that's simply because the parameters beta were in the exponential, as arguments to an exponential, in the definition of the probability distribution. And that gave us expressions which are non-analytical in the way we have been used to when we did linear regression, where we had a very nice expression for the parameter beta, which then could simply be obtained by inverting a matrix. So this is not the case now. And due to the problem which we have to solve these equations, which are going to be coupled, non-linear equations. We have to solve them iteratively. And that's the basic approach to a set of coupled non-linear equations. So it's non-linear in the unknown parameter beta because we have this probability which is defined through an exponential. So we cannot single out beta as a standalone parameter like we did in standard linear regression. And the standard approach in basically every field of science where you have this type of equations is to solve them iteratively. And that's where methods like Newton-Raphson's method come in, because we are looking after the roots of a function. The roots we want are the zeros of the gradients. So we are going to try to find the zeros of the gradients. And all these methods, they rotate around us being able to evaluate these gradients and essentially drive them to zero. And that leads to a whole family of different methods. And as you saw last time, we have a parameter which we introduced, and I'm going to repeat these things, which are related to the second derivative of the objective function, which is again the first derivative of the gradient, which we call the Hessian matrix. So let me remind you quickly of some of these things, and then we're going to jump a little bit back and forth between the whiteboard and programs which we are going to run. Now, for project number 2, we're actually going to start with you writing a program for optimizing standard linear regression, but doing it numerically with a gradient descent. That means that instead of you inverting a matrix, you're going to find the zeros of the gradients by implementing a kind of Newton-Raphson method or approximations to that. So that's the warm-up part of project number 2. And then you will need this when you're going to write a program for neural networks. And as I said last time, what we do now is a kind of stepping stone towards us implementing these gradient methods in the setup of a neural network and our first encounter with deep learning methods. So project number 2 is essentially you writing a code for neural network. And then you will need the gradient methods. And there is a famous algorithm which is called backpropagation, which simply deals with you implementing a gradient descent method or one variant of it. Now, the problem which we are going to face is that often we have zillions of parameters, which means that these non-coupled equations which we have to solve, they involve many, many parameters. And then it's pretty common to replace a standard gradient descent, which is going to require a lot of floating point operations, with something which is called a stochastic gradient descent. So this is also something we will introduce. And then there are ways to estimate this learning rate or this Hessian matrix, which we replace with just a constant. And that leads to many, many different schemes like adaptive gradient, where you learn the value of this learning rate iteratively. You have the root mean square propagation. There's a very famous method called ADAM, which, as I mentioned last week, has 150,000 citations in less than 10 years, which is quite a lot. And many, many other methods. So this is essentially what we will try to cover today and also next week when we begin with neural networks. So see this as a kind of motivation for one of the basic ingredients you need to set up a code for a neural network. Okay, any questions to the kind of overarching view of things? So I wanted quickly to remind you of some of the things we did last week. So as I say here, the optimization is a central part of any machine learning algorithm. So the thing we did last week was actually to derive, using this maximum likelihood estimators, the equations for logistic regression. And then we started with replacing the function f of x with a probability. And that probability contains only the probability of yes and no. So we were looking just at a binary problem. So false, true, yes, no, 1, 0, etc. And then we defined a probability where we use this function, which is normally called the logistic, or you will find the name sigmoid function, which is a way to approximate this probability. It's just an approximation, it's a model. You can make it more complicated. But we use this one to motivate the need for calculating gradients. So, because this is a case where you don't have the nice analytical expression. And when you did that, you had a probability for 1 and a probability for 0. And the probability for 0, since we have only 2, is 1 minus the probability for 1. And this is easy to deal with. And when we did the calculations last time, what we ended up with was something like this for the first derivative. And then we just interchanged sign here. So we got a plus, and then we had p minus y. And p is this probability, is a vector. And in this case, when we only had 2 parameters, we end up with obviously only 2 equations, one for the parameter beta 0 and one for the parameter beta 1. And I'm going to repeat some of this on the whiteboard. And then what we also did was to calculate this Hessian matrix, which is the second derivative. Now, this W is a matrix which is diagonal, which contains the probabilities. Now, the probability is always positive. And that matrix, you can actually show that that matrix is actually positive definite, which means that we are again dealing with a convex optimization problem. So remember that when we calculated the second derivative for the mean squared error, the cost function we had for ordinary least squares, then that was given by the design matrix transpose times x. And when we did the singular value decomposition analysis, we could then show that all the eigenvalues of x transpose times x are positive. And that means that we are dealing with a convex optimization problem. And the same thing applies for logistic regression. So these are what we normally call nice and well-behaved problems. So convex optimization clearly defined, there is a minimum. When we move into neural networks, we have no idea whether we have a local minimum, a saddle point, a global one, etc., etc. And we are going to have zillions of parameters. So Next week and the week thereafter, we are going to leave our comfort zones with the nice and well-behaved problems. And then we will have to deal with the problems where we may not know if we have or where we are in a multidimensional surface. If the minimum is a saddle point, which is not what we want, or whether it's a local minimum or global minimum. Now, the thing which we then did was actually to derive what we called Newton-Raphson's method. And the kind of equation which we ended up with, actually these type of equations. And the new beta value is given by the old one. And this quantity here is now the second derivative, it's the Hessian. And the Hessian is now given by this matrix in this particular case. And then I have the gradient, which is now given by the expression which we calculated. And everything here is calculated with the old value. And this iterative scheme is something which you may have seen for just one variable. And I guess Newton-Raphson's method does ring a bell. And we derived that last time. So I'm going to bring back the elements which we did in order to derive it. Because there are some mathematical aspects which are useful to think of. And what we end up doing then, as you can see, you have to invert the matrix. Now, these equations which we derived last time, they were based on us Taylor expanding the cost function in terms of the difference between the true value we want, the optimal value for beta, and the one from the previous iteration. But then we truncated this Taylor expansion at the level of the second derivative, which is given by the Hessian matrix, this quantity which you see here. So if you have only two parameters beta, there will be one equation for beta 0 and one equation for beta 1. And this matrix, which you have to invert, this one is going to be a 2 by 2 matrix. So for that specific case, we could actually invert the matrix using Newton's method. Now, keep in mind also that we truncated the Taylor expansion at the level of the second derivative. If we didn't do that, we would have to include third derivatives, fourth derivatives, and so on. So we are assuming that quantities beyond the second derivative are negligible. So that's an approximation we did in order to be able to obtain Newton's method. So Newton's method actually truncates your Taylor expansion. It is based on a truncation of a Taylor expansion. And that gives us these equations. But you made an approximation already. And this approximation may be good or may be bad. Now, the reason why I stay with this kind of overarching picture still is because the ideal now is to solve Newton's equations. What we cannot do typically with neural networks is actually to invert that matrix, because that matrix is going to involve zillions of parameters. Even for simple cases, which we will look at in the next weeks, this matrix is going to be a matrix of dimensionality 100,000 times 100,000. And if you have 100,000 parameters, you will have to rewrite that equation there with 100,000 lines, one for each parameter. And for every parameter you need, for every iteration, and you will typically have hundreds of iterations, you need to invert a matrix of dimensionality 100,000 times 100,000 as an example. This means that what's standard is actually to approximate this second derivative with a parameter. And that parameter was what we labeled the learning rate last time. So I'm going to go through a little bit the things which we discussed last time and just quickly remind you of some technicalities. So let's do that. And then we go back to the slides and we are going to look at the implementations and some specific calculations. And after that, we are going to see how we can speed up the convergence of a standard gradient descent method. Any questions so far? You can replace everything here with the ordinary least squares. And the examples you will see here actually based on ordinary least squares and ridge regression. Yeah, there's a question. So here we truncate at the level of the second derivative. So we made a Taylor expansion, and that's what I wanted to bring up now, just to remind you of that, what we did last time. So let me bring up what we did, and then it will be a little bit easier to see the different links to Newton's method. So what we had last time was that we took and Taylor expanded the cost function around the optimal value. So we have decided that we want to maximize, this is for logistic regression, so minimize, that's what we did. So beta, element of P with P elements, and then we had minus log, and then we have this probability distribution with a domain of events which we had with a given beta. And this is the quantity which we optimized. When we did that, we found the expressions, and let me just quickly remind you of that. So we find the expressions for the derivative of the cost function. So this is our cost function, C of beta. We calculated these quantities and we labeled them just as a G for our gradient. And then we have the Hessian matrix, which is the second derivative. So right now, I'm not going to write down the specific expression for the matrices. I'm just introducing the symbol here. So the thing we did then was to perform a Taylor expansion around the optimal value. Perform a Taylor expansion and this was done around the optimal value beta. Beta hat. So what we do then is that we make a transformation around a variable beta minus some beta of n. And beta of n is then going to represent the iteration before we found the optimal value. And when we did that, you know that when you Taylor expand, if this is a scalar, or it's just a function which depends on a one-dimensional variable, then we would have a pretty simple expressions. But since these are going to be vectors and matrices, we have to be a little bit careful. The final function which we get is a scalar. So that means that we have to take the inner products of different vectors, and we have to compute the transpose of a vector times a matrix times a vector in order to get a scalar. So we have to be a little bit careful when we write this out as a matrix. And what we did then, since these betas are now vectors, so this is the optimal one, and that's going to be a function of this value from the previous iteration, the previous value, which is close to the optimal value. And then, since these are now, so C is a scalar, but then all the quantities we are dealing with are vectors and matrices. So then we have to be a little bit careful. So then we have C, and this is the gradient calculated at the nth iteration. And this is something which was then given by beta minus beta n. And now when we come to the term which involves a second derivative, we have also to convert into a final scalar. So we need then to write this as a vector transposed times the Hessian matrix evaluated at iteration n, because that depends on the unknown parameters beta. And then we had a beta minus beta of n. But then we have higher order terms. And what we did last time was actually to leave out the higher order terms. And we also introduced a new variable, b, which is a vector which is given by the optimal ones minus those from the previous iteration. And then we could rewrite this term C of beta, and we approximate it to second order, to the second derivative. And this contains G of n, and this is transposed, multiplied with a vector B, and plus 1/2 of B of T of H of n, multiplied with B. And then we stop at the second derivative. And when we then take the derivative of that equation, so we take dc dB, and we want to drive that to 0, what we find then is that we get G of n, so plus this H of n times B. And now we are using these expressions we had for calculating derivatives of vectors and matrices. So this goes back to one of the exercises in the beginning of the semester. So I'm not showing all the intermediate steps because we have done that before, some of this. And what we do then, when we now remember what this B is, so since this B is given by this expression which you see here, we can rewrite this equation here in the following way. So if we take this expression and rewrite it, what we get then, we can isolate beta, the optimal one, and we are going to call this n plus 1. So that will be given by beta of n minus, and then I have H of beta calculated at the nth iteration. So this is the matrix we need to invert. And this is multiplied with the vector, the gradient, evaluated at the nth iteration for beta. So this is Newton-Raphson's method, nothing but that, where we truncated the Taylor expansion at second order. And everything which we are going to do in machine learning starts with this equation. So if you can invert a matrix, what people normally would do then is actually just implement Newton-Raphson's method as it stands. Now, there is one drawback here, and that is clearly if you have many points, data points, this becomes expensive numerically to calculate all these quantities. And that's what approximations like stochastic gradient descent kicks in. And that's something we will come back to later today. Now, what you see here is more a case. So in more general terms, this is actually our C of beta, which is now replaced by a function f of x, which we could write as something like this. So it would be a general function where I could set, let me just find my cheat sheet here. So it could be a function with a constant plus some variable g. I'm writing these as vectors now, times x. X is a vector, plus 1/2 of x, and then there's a matrix A times x. So this is a problem which is actually the same as the one we started with. But you could now think that your cost function is given in this way. Okay? So that's an assumption we're making. And if you look at this problem here, this is a problem which you probably have seen before, because if I take the derivative of this d of x, this becomes, if you want that to be 0, that is the same as a times x plus g. And that leads to a famous problem in linear algebra, where we simply have that the unknown x is the unknown quantity, x is given by minus, and then they have the inverse of that one, times g. This is a problem you probably have seen in linear algebra. So you have a matrix A, you know the g, and then you can find the unknown quantity x. So this is just another way of expressing that equation, which you have seen probably before in many linear algebra applications. The In our case, this G is going to be the gradient, and this this matrix A is actually the Hessian matrix. Now, there's one thing more which we can do, which is useful. So if we now look at the solution which we have, so we found that beta, this beta optimal, which we label as a beta of n minus plus 1, we can rewrite this one in terms of the previous value. So instead of taking the Hessian, we are going to replace that one with a variable. So this is a parameter which we introduced last time, which we call the learning rate. And all of the methods which we are going to look at, they deal with ways of approximating this learning rate. So the brute force way of doing this is simply to set up an array of learning rates, the same as you've been doing with ridge regression, where you have an array of parameters lambda. And then you just run through the calculation with different values of this parameter gamma, and you find the parameter gamma which gives you the best mean squared error, for instance. That would be the brute force approach. And actually many people do that, because sometimes it can be very expensive to try to update this parameter gamma as you move on in the calculations. And what you will see are tons of ad hoc approaches to modify it, till more refined ones. And there is a big discussion now actually in the community, and there is something which we are going to come back to a little bit later as a digression, and this is called the Fisher entropy, which is a way to estimate the Hessian matrix, which circumvents many of these more ad hoc methods, which are very popular in the literature. But the brute force way is simply to make an array of values of gamma and simply pick the one which gives you the best result. That's a very common approach. So this learning rate is now a parameter on the same footing as this lambda, which you have in ridge and lasso. And what you will see is that many of the methods we're going to deal with, they add this penalization parameter or shrinkage parameter, as we called it, from ridge and lasso. So you will see that in neural networks, people would also apply a similar additional terms with a hyperparameter lambda. And then you would have a new parameter gamma. And then you would have many, many other parameters when you do cross-validation. You would have the number of folds. When you use stochastic gradients, you have to decide on further parameters. So at the end, you're going to fine-tune something like 5 to 10, 15 different parameters to find the best optimal mean square error. But there are two parameters which stand out. This one, the learning rate, because that influences the value of the gradient. And the gradient is very important because that's the way you find the optimal values. And then there's going to be the hyperparameter lambda. And these are typically the parameters which people tune first. And when they found a good set of these parameters, then they move on to tune the other parameters. But as I said to some of you, I mean, many people feel a disappointment when they just enter this jungle of different parameters. But they are, in a way, they are, I would say like this gamma is a reasonable parameter. This is simply because you don't want to invert a matrix, period. So if you now look at this learning rate, one of the things we can do now is to Taylor expand around this expression. In the previous case, we actually had the Hessian matrix, but now we're just going to look at this learning rate. So let's Taylor expand again. C of beta again. So what I'm going to do now is simply to expand around this value which you see here. So I'm going to calculate this C of beta of n. And you will see just in some few moments why this is interesting. And this gives me now C of beta of n. And then I have minus, and I have a gamma, and then I have this G, evaluated at iteration n transpose times g of n. So now instead of putting beta, I'm plugging in this gradient which I have in the expression for beta. And then I have plus 1/2 of gamma squared. And then I have a g of n transpose times this Hessian matrix. This is the second derivative. Remember that. So that has to be there, like that. And then we truncate at the second order here, at the second derivative. So it means that we leave out this one, and then we should put an approximation sign here to be consistent. So if you look at this one, what you could say now is that you have an expression in terms of gamma. So can I use this Taylor expansion to find an optimal gamma? And this is actually something you can do. And this is close to other methods, which some of you may have met. So who has heard of steepest descent as a numerical method to find optimal values? So steepest descent is going to give us an expression for this parameter gamma as a function of the iterations which we're making. And it's pretty close to what we have here. So this contains some of the basic philosophy behind steepest descent. So what you get then, when you take the derivative with respect to gamma of that expression, to gamma, what we get then, and now I'm just going to introduce some shorthands. So I'm just letting the gradient at iteration n be given by g. And then I also let the gradient at iteration, the second derivative at iteration n just be replaced by h. So if I take the derivative, what I get then is an expression for gamma, which is given in terms of this gradient multiplied with a gradient, multiplied with h, the second derivative, and multiplied with a gradient. So this is me just taking this Taylor expansion, which you have, and I take the derivative because I want to find what the optimal gamma. Now, this is the same equation for steepest descent. It's just another way of deriving that one. So in the lecture notes, you will also find expressions for the steepest descent, which is a widely popular method for finding the zeros of a function. And what we've done now is something which is also interesting, because we could assume that h times g, that these g's are eigenvalues of h. So if we do that, then we know that this gamma is simply given by g transpose times g divided by lambda times g transpose times g. So that is 1 divided by lambda. So we have a recipe then for finding the optimal gamma here, which is given by the eigenvalues. But now keep in mind that this approach here is not the best one, because H, the matrix H, can be a monster matrix. So if this is 1,000 times 1,000 matrix, you would have to diagonalize 1,000 by 1,000 matrix every iteration. You see that? And this is something you would like to avoid. So this kind of recipe means that you have to calculate the Hessian matrix, which then would involve, if you have 1,000 parameters, it would involve all the combination of these derivatives to second order. It's going to be 1,000 times 1,000 matrix. And you would have to diagonalize that to get this lambda. And this is clearly something which becomes expensive computationally. So everything we are going to discuss now is you striking a balance between the number of floating point operations you're willing to spend and the accuracy of the results. So it's always us at the end who has to make, we have to make that kind of choice. Any questions so far? So I'm trying to give you the kind of main overview of what is going to come, so that you see the central elements in many of the approximations. So in this specific case, we could calculate the gradient, but remember now that the gradient is evaluated at iteration n, and you do that for every single iteration. So this recipe is nice, but it is numerically very expensive. There are other methods, and some of you may have heard of the favorite method for finding the zeros of a function, which is called conjugate gradient. Has anyone heard of that? That's one of the more popular methods. That also requires that you have to evaluate a matrix like the Hessian matrix, which again is expensive. And that's why at the end, everything which we are going to deal with is going to look like this. So beta of n plus 1, the ideal value when it has converged, is a beta of n minus some gamma of n multiplied with a gradient at iteration n. So sometimes we just leave gamma as a constant, and other times we are going to update this gamma in different ways. And the more popular ways of dealing with that, one is called adaptive gradient, and that works very well if you have a convex problem. So ADA for adaptive. And then there is something which is called root mean squared propagation, or just RMS prop. And then we have ADAM, which is adaptive with momentum. But the plane gradient descent, the most stupid way you can implement it, is just based on us having beta of n plus 1 is equal to beta of n minus a fixed gamma multiplied with g of n. And that's the kind of method which we are going to look at now, and some of the first implementations. So when we are going to start with project 2, we are going to start in a soft way, in the sense that we want you first to write a code for doing gradient descent and what's called stochastic gradient descent. So there are additional things here which you can implement here. So all of these methods can be implemented here. You will have something which is called momentum, which is actually included in this ADAM. So the M here stands for momentum. And I will explain to you after the break what this means. And this is something we can easily implement, and it's normally done. I like to call this memory because you keep information about previous iterations. And that is a standard trick which is used in all these kind of iterative solvers. So momentum is one simple way which can allow us to speed up the calculations of the gradients. Because what we want is actually that n, the number of iterations, shouldn't be more than a few hundred. And this is one of the painful things which many of you have seen now with Lasso. Because Lasso is solving these optimization problems using Newton-Raphson or some families of Newton-Raphson methods. So there are approximations, there's something called quasi-Newton methods, and there are actually tons of different ways of approximating the Hessian. So you can see that this is a huge field in the theory of mathematical optimization. So if this is something you like, there is lots of interesting things to explore. So the thing is that you would like to avoid having too many iterations, and you've probably gotten this message when you run Lasso with scikit-learn that you didn't have enough number of iterations for convergence. Because typically the kind of test you have for the convergence here, so the convergence test, the most typical one is that you take the absolute value of these two vectors, the previous iteration and the new one, and you want that one to be smaller than some epsilon. And epsilon can be something like, let's say, 10 to the minus 8 or 10 to the minus 10 or whatever. So you calculate the absolute value of the difference every iteration, and then you just compare that to a convergence criterion, which you have decided upon. So scikit-learn, I always have to look up the manual, but scikit-learn has a convergence criterion, and it has a number of default iterations. which you may need to change if you haven't reached convergence. And probably, so how many of you have gotten that message when you run lasso? Yeah, I see. There's a good fraction of people at the lab. I saw several people which got that message. So that means that you would have to increase the number of iterations. But this again becomes expensive. So everything which we're talking about now rotates around the accuracy you want and the number of floating point operations you're willing to spend. Any questions so far? So if we continue a little bit, if you look at that specific value, there is actually a specific convergence criterion. And you can actually, so I'm just stating it. So there's an explicit convergence criterion. And that is that gamma should be smaller than 2 times lambda max. And where lambda max is the largest eigenvalue of the Hessian matrix. So H is the Hessian matrix. And then there are actually things you can study. And for those of you who are more into linear algebra and may have seen that, if the minimum and maximum eigenvalues are very different, then the convergence can be slow. And the convergence is normally something which is determined by the condition number, which is the ratio between the maximum eigenvalue and the smallest eigenvalue. So if there's a large difference between these, then convergence can be slow. And you will see that in some of these practical applications, which we're going to do now. Let me see, there was something I wanted to say. No, okay. So I wanted to jump back to the Jupyter notebook, if that is okay. So let me do that, and then we are going to look at some implementations. So in the slides, what you will find, in addition to some basics about Newton's method and so on, and you can see the things here which come up, which relate to the Hessian and so on. Here we have steepest descent, which is another method which is widely used, but that requires that you can actually calculate the Hessian matrix and multiply it with the gradients. But in addition to these things about convex function, which I will leave to you, so here's the derivation of the steepest descent. And I wanted to move down a little bit. These are methods which all, both the conjugate gradient method and the steepest descent, are all methods which require, if you look at the steepest descent method, as we mentioned previously, it requires that you can calculate the Hessian matrix and multiply with the gradient, and then update your parameter gamma, which are here called alpha. And X is the same as beta, which we'll be looking at. So being able to calculate that one means that you could use either steepest descent or conjugate gradient method. But the problem we face is that the dimensionalities are going to be too large. And we want to avoid that. And in particular, when you do neural networks, the number of parameters you're going to have are so many that it's very unlikely that you will be able to calculate the Hessian matrix. So what I want to do now, after this kind of general words, is to look at specific examples. And this is an example which you've seen many times. So this is us setting up a first order polynomial. And we are going to use linear regression. But now we are simply going to implement our own gradient descent in its simplest possible way. Okay? So what you can do then is to set up a data set. Just again, this kind of vanilla sets, a first order polynomial with some x values. X is defined between 0 and 1, multiply with 2, which means that x takes values between 0 and 2. If we do the gradient descent, we know that since we are fitting a first order polynomial, this is the way the design matrix would look like with the intercept baked in. So this is something we've seen before. So we have the 100 points, and this is the explicit design matrix. The cost function is then given by these terms which you see here. So it runs from 1 to 100. I have my first order terms, beta 0 and beta 1, and then I subtract minus beta 0, beta 1 multiplied with y plus y 1 here. So I'm just squaring this expression here. So this is basically what we've done before. But now I'm setting it up explicitly. I take the derivative, and you see now that since I have only two parameters, I get two rows or two values for the gradients. So one is a derivative with respect to beta 0 and one with beta 1. That sound reasonable? So I have only two parameters. And this is essentially what we've been doing till now. And the gradient looks like this. And we've seen that before. So this would be the equation I need to implement in my code. Then one thing I can do here is actually to calculate the Hessian matrix, because that is simply the derivative, the second derivative with respect to beta 0. And then I have the cross terms. So this is essentially my Jacobian. So my cross terms, which are here, and then the final one for beta 1. And then I get this expression here, which we have derived earlier. And then we can set up a simple program, and where what we are doing now is simply to iterate beta 0 and beta 1 as a functional number of iterations. We have a fixed learning rate, gamma, and then we keep going here for different types of iterations. And you can choose to set the gamma equal to 0.01, or you can choose the eigenvalues from the Hessian matrix. And then you could stop iterating when this gradient, so you can make different tests. You can either compare the new values of beta with the previous one, or you can calculate the gradient. So I just leave you with a question during the break. Which one would you prefer? Would you prefer to calculate the gradient, or would you prefer to calculate the difference between the new beta values and the previous one? So think of this in terms of number of floating point operations. So assume that your gradient has 1,000 values of x and two parameters. You can evaluate how many floating point operations that is. And your beta values are only 2, so you need only to compare two values. I'm always giving you the answer here. So that test is inefficient. So you would typically just compare the beta values, because the evaluator gradient is going to take much more time. Okay, so should we take a small break? Is that okay with everybody? And then we look, yeah, you have a question. So I'm calculating the gradients, but then I would calculate the gradient at the next iteration, because that's the gradient at the previous one. Yeah, so if you do, you have calculated the gradient here, but if you then calculate the gradient at the new iteration, that's the one you would like to evaluate. Yeah, you would do k plus 1 typically. Yeah, so that's more time consuming. And you see also the bottleneck in these calculations. If you have many data points, the gradient will be expensive to evaluate. And that motivates something like stochastic gradient descent. But after the break, we're going to discuss something which is called momentum gradient descent, which is a way to speed up the plain brute force gradient descent. We'll take a small break. Is that okay with everybody? Let's do 15 minutes, eh? So this kind of case where we fit a second order polynomial is actually not that different from what you are doing project number 1 here, because typically you would have something like, if you fit, let's say, a second order polynomial, you would have 6 parameters for this Franke function. And that means that your Hessian matrix would be a 6 by 6 matrix. And then you would have 6 gradients to evaluate. So that is still what we would call a baby case. This is a cases which you can solve easily. And you could, in that case, you could even then calculate the Hessian matrix, because it wouldn't be that time consuming. But as soon as you go into dimensions of thousands and thousands of parameters, this becomes expensive computationally. And that's why we introduced this learning rate. So what I've done here is actually just to implement a simple, stupid learning rate and just use that one and see what happens. And let's take a look at the code here, right? So the code which you see, the first one is not very fancy at all. So I have this data set with 100 points. One thing which I'm doing here is actually to use the Hessian matrix to guide me and its eigenvalues. So what I'm doing now is to calculate the Hessian matrix, and I get the eigenvalues of that matrix. And then I'm going to use the max eigenvalue and just see what happens. Okay? Here, I could actually have calculated the inverse of the Hessian matrix in every iteration. But now I'm going to use the maximum eigenvalue. And so that means that it's 1 divided by the maximum eigenvalue. So in principle, it's actually 2. So eta should be smaller than 2 times the 2 divided by the maximum eigenvalue. But now I just put that one to 1. And if you look at this case here, you see now I started with the values and I had some noise. If I take away, let's take away the noise, because then everything is going to be nice here. So if I take away the noise, I get 4 and 3, perfect. And one of them is the, so I do my prediction here. The first calculation, I calculated by just using the standard matrix inversion algorithm, which we have implemented in project 1. So this is what you've been doing till now. And then the next step here is me changing it. And I've been a little bit lazy here because I didn't put in a convergence criterion. If you look at the eigenvalues are between 0.3 and 4.3, something like that. So let's change this parameter. Let's now suppose, let's see what happens. If I change this parameter to something which is, so I said 4.3. So let's say we put it just eta to 0.1. Let's see what happens. So I skip the eigenvalues which come from the Hessian matrix, and that seems to be working okay, because that would be okay. If I now make it larger, I'm getting ambitious, then you get not a number. So I made my step size way too large. So that means that I will jump away from where I have the minimum. So what you saw in that specific case, if we now go back to the whiteboard, so let's just try to analyze that case a little bit more. And let's switch to the whiteboard. So what happened in that specific case, suppose now we have a very simple function, which looks something like this. And here is where we have the optimal value of beta, the optimal one. And then I start with a guess here. So that's my first iteration. And I start with a guess here. And then I'm going down here by the gradient. So I have my gradient minus gamma times g, which is driving me down towards the minimum. But if I make this too large, I may actually jump down here. That will be the first one. And then next time, I may go up here. And then I may go away here. And then it will never reach that minimum. And that was what happened here. I made my step size too large. So that's a typical example of a case where the step size which I chose didn't make sense. Now, I can obviously make the step size very small, just to be safe, but that could easily mean that I would not be able to reach the minimum. So let's take a look at that. So suppose now that I start here, I start this point, and then I move to this point, and then I go in many small steps, and after a given number of iterations, I'm here. So I haven't found the optimal value. That's another situation which may occur. So like in this case, where you can calculate the eigenvalues of the Hessian matrix, you can guide the value of lambda, now gamma, by the eigenvalues of the Hessian matrix. But in general, you would have to set up a grid of values and play around in the way we are doing here. So, and you saw in that specific case, when I made my step size too large, it didn't converge at all. So let's make the step size very small and then limit also the number of iterations. So suppose I say that I don't want to give you more than 50 iterations, and then I make my step size very small. So let's see what happens then. Let's say we have 10 to the minus 4, and I have only 50 iterations. And there you see the values of beta. So these are the ideal ones, which I get from my code. And here you'll see the one which results after 50 iterations. And then I made a step size which was very small. And many of these algorithms have often between 50 and 100 iterations as a default value. So if things haven't converged, it could be simply because you've chosen this too small. So if I now exaggerate and say I want to do 10,000 iterations, which is a waste of time, even then I'm not getting there. So, but I'm getting closer, but I'm not getting the numbers which I wanted. So you see clearly the dependence on the number of iterations you want to do and the step size. If I then change this one to, let's say, 0.01, and then I do 100 iterations, let's see what happens then. We are almost getting there. So if I make a step size of 0.1 and do 100 iterations, I'm closer, but I still need some more iterations. So I would need, let's say, let's try 200. Yeah, it's getting closer to 4 and 3. So I need more actually. So if we do 400 iterations, then it's getting close to 4 and 3. So this is the kind of things which we will have to live with, especially when we have a multi-dimensional beast, which we don't know whether we are located in a saddle point, local minimum or global minimum. Does that sound clear? So the learning rate plays an important role as a parameter, and we need recipes by which we can tune it. And what you will find in the slides here would be examples we're using scikit-learn. This is something I will come back to, stochastic regressor. So I'm going to explain that a little bit more later. Here you have examples with ridge regression. And in that specific case, when you calculate the Hessian matrix for ridge regression, you will see that since this is a positive definite one, these numbers lambda are always larger than 1. So that means that the Hessian matrix is always positive definite. So the stationary point is a minimum. And the ridge cost function is actually a convex function, being a sum of 2 convex functions. So therefore, the stationary point is actually a global minimum of this function. And it's pretty easy to implement it. You can set up the matrix x transpose times x, and then you need to add the diagonal matrix. You can calculate the Hessian and get the eigenvalues and let the Hessian matrix guide the setup of the learning rate. So in this typical example, this is what you would get. So these are the values which matrix inversion gives you, the way you've been implementing this in project number 1. And this is what my gradient descent gives you. And you see now that you are almost the same at some leading digit. You don't get exactly the same because now you're calculating the gradients numerically by iteration. So it means that you will not get a perfect agreement, especially here when you have noise. When you often have take away noise, then often this will give you a better result. But you will see something like this. You will see a small difference. Like in this case, the difference is at the 6th digit after the decimal point. And that's something you have to decide whether this is acceptable or not. So if we summarize this, if you use gradient descent, there are specific limitations. It's very easy to implement. So the gradient descent is deterministic. If it converges, it will converge the local minimum of a cost function. So in machine learning, we often deal with extremely rugged landscapes with many local minima, and this can actually lead to very poor performance. Now, it's also very sensitive to initial conditions. Unless the matrix is clearly positive, definite, the Hessian matrix, it will often be very sensitive. And since you're dealing with Newton's method, it's actually Newton's method. I don't know how much you remember from that when you saw it the first time. Newton's method is actually very sensitive to the initial conditions. And you can have a Newton method because everything you're doing now is based on Newton's method. And it may not converge to the desired result, or it may not converge properly within a given number of iterations. So Newton's method is sensitive to the number of initial conditions, to the values of initial conditions. Now, another point which kicks in is that they are sensitive or they are expensive to calculate. And in many cases, this loss function, cost function is the sum of terms with one term for each data point. If you do linear regression, you have something which runs like this. And for logistic regression, the square is replaced by the cross entropy, which we discussed last week. And to calculate the gradient, we have to sum over all n data points. And doing this at every gradient descent step can become extremely computationally expensive. An ingenious solution to that is to calculate the gradients using small subsets of the data called mini batches. And this is what leads to stochastic gradient descent, which we will come back to pretty soon. It's very sensitive to choices of learning rates. So it's not only initial conditions, but it's also the learning rates. As you saw, these specific cases which we played around with could give us a poor result if we had a too small value or too large value. And another thing which it does, the simple way we have implemented it, is that since the learning rate does not depend or has information about the gradients, it means that it has the same, it gives the same value for all directions. When I say directions, you have a parameter beta 0, beta 1, etc. And each of these gradients, they point in a direction. But gamma does not, it just has the same value. So that means that when you look at it, it treats this parameter space is actually uniform. So if you use the gradient descent, the learning rate is the same in all directions in parameter space. And that means that the maximum learning rate is set by the behavior of the steepest direction, and that can significantly slow down training. So ideally, we would like to take large steps in flat directions, and then you would like to take small steps in steep directions. But the gradient descent just runs with a plain equal parameter for all the directions which you have. And this is something which we need to modify. So the simplest way we can modify that one is actually to include momentum. So let's go back to the whiteboard and see what this momentum actually means and look at how we can implement it. And at the end, you will see that this is a very easy algorithm to implement. So let's switch back to the whiteboard and look at the gradient descent with momentum. So this is inspired from the solution of differential equations. And one of the famous differential equations is actually Newton's law of motion. And that's where the word momentum comes from. I like to call this memory-based methods. And you will see why memory can also be a useful name for it. But let's take a look at how we can get to the gradient descent with momentum. So one of the convergence of this gradient descent can actually be slow if the curvature of the optimization surface is such that there are regions which are poorly scaled. And the curvature is such that the gradient descent steps jumps between various values and approaches the minimum in very small steps. as you also saw from some of these examples. So what we're going to do now is to look at the gradient descent with the momentum. And that's something which can speed up. So let's take a look at a famous equation. And we're going to look at Newton's equation of motion. And that's where the name momentum comes from, equation of motion. And we know that there is a force which acts on the system. So you would have m times the second derivative. So we're just looking at a one-dimensional system as a function of time, plus some drag or friction term. So you have a velocity-dependent term. And this is equal to a force, f of x, which is actually the gradient, the negative gradient of a potential. So this is Newton's second law with a drag or friction term. And then there is the acceleration, which is the first term. Is anyone who's never seen this equation before? Okay, this is, yeah, I guess everybody's seen that in one way or the other one. This can be, it doesn't need to be Newton's equation. It could be another type of system. So the mu is just a friction term. And then the force which we have is now given by the gradient of a potential. And then the way we typically solve this equation is that we discretize the equations. So we discretize the second derivative and the first derivative. And you know that when you discretize with respect to time, so we would have a time step, delta t. And that means that I have a dx, the second derivative, I would approximate that one with a value at a time step t plus a delta t plus x of t minus delta t minus 2 times x of t divided by delta t squared. That's the standard approximation for the second derivative, which actually you shouldn't use. You should use automatic differentiation. Because if you use that one and repeat derivatives and use that one to calculate third and fourth derivative, you're going to go get wrong results. But this is an approximation which you will see in essentially all numerical solutions to differential equations. And this is essentially the manipulations of Taylor expansions. You may remember that perhaps. So Taylor expansions pop up everywhere. And then you can discretize, if you use a forward Euler, you discretize the first derivative, dx dt, and that's going to be given by an x of t plus a delta t minus x of t divided by delta t. So this is just a forward algorithm. And then I'm going to put this back into the differential equation. And then I'm going to rewrite the differential equation a little bit. So let's take a look at how this ends up in the differential equations. So we rewrite this equation here with these approximations. So everybody's gotten it? Okay. So now we rewrite that differential equation. And if we do that, we get simply m. And this is multiplied with x of t plus delta t minus 2x of t plus x of t minus delta t. And this is divided by delta t squared. And then I get this term plus mu. And then I have x of t plus delta t minus x of t. So this should be a subscript here, divided by delta t. And this is equal to minus delta v of x. So this is the gradient of the potential. And then I make a definition of a new quantity. So I define x of t plus delta t. This is the difference between x of t plus delta t minus x of t. And then I have my delta x of t, and that is given by x of t minus x of t minus delta t. Then I can rewrite my equations if I now separate out this term delta x of t plus delta t here. I can rewrite that one in terms, and I multiply away delta t squared. So this is a delta t squared, and this has an m plus mu times delta t, and this is multiplied with delta v of x, plus a term which goes like m divided by m plus mu of delta t times delta x of t. And then I'm going to simplify this in the next slide. So this is just a rewrite of the equation, and you will see now that with that rewrite, we can introduce this concept of memory or momentum, as I mentioned. Okay, everybody seems to have gotten it. You will also see everything on the whiteboard. The whiteboard notes are always uploaded after the lecture. So what I will do next is now to define a new parameter, delta, which I call for m divided by m plus mu times delta t. And then I have a new parameter, which I call gamma, which is simply this delta t squared divided by n plus mu of delta t. And that means that I can set up this delta x of t plus delta t. And I have this parameter, which is minus gamma of delta v of x plus this delta of delta x of t. Now, if you now look at the first two terms here, this one, that is nothing but the standard gradient descent method, which we have seen before. So what we have there is actually, if I rewrite it, what I have then is that this is nothing but y or x of t plus delta t, the next value. So I can reshuffle it, and then I have x of t minus gamma of dv of x, and this v of x is actually calculated at this value t. So this is a v of x. And then I would have this additional term plus delta times delta x of t. So if you leave out these parameters, the explicit values which you have, you see now that if you take a closer look at this one, this is delta times x of t minus x of t minus delta t, the previous value. So the first equation which you have, this one, this is nothing but the standard Newton's method, which you have seen before. So you have a gradient, which is here. You have this gamma, which could be thought of the learning rate. And then you have the value, the previous value, and then you have the new value. But then, if you take a closer look at this one, what you will see then is that this new value is something which now keeps the present value, but then it has some memory of what happened before. So if you take these Newton's equations with this damping term, this friction term, which is proportional to the velocity, this is normally called a momentum term, because the momentum is proportional with the velocity times the mass. So that's why we have this name momentum, but I like better to call this a memory term, because you keep a memory of something which was there previously. Now, the thing which is interesting here, if you're looking at these gradients, if there are large oscillations between x of t and x of t plus delta t, then clearly the convergence can be slow. By bringing in information from a previous step, you then smooth out the large oscillations in values between x of t and x of t plus delta t. So this is the effect of this momentum term or memory term, that you can actually dampen large oscillations between the value x of t and the new value. Now, one thing you will see also is that depending, so this delta t is a fixed parameter, but this mu can become large or it can become small, and the same here. So you see that this quantity here, depending on the value of mu, it means that this is something which will take a value between 0 and 1, this parameter delta. So you can, mu is a positive quantity, it can be 0, and then you will have the value 1, but it can also be large, and then you will actually have something which can be closer and closer to 0. So this typically, this value of delta, when you look at it, so delta takes a value typically between 0 and 1. And this is a parameter which you can choose. And this becomes a new parameter in your optimization. And this is a normal trick which is used in this kind of iterative methods. So I use it regularly when I'm solving nonlinear equations, because this is a set of nonlinear equations. And it can actually speed up the convergence of a standard gradient descent. And this is a simple way to actually improve the gradient descent. And it gives you less optimization steps. So typically the parameter delta is something you would have to tune, but you can take by default, you can just put it to a half, and then you would have a memory of a previous iteration. So I like to call this not a momentum term, but I like to call this a memory term, because you keep an information about previous iterations. Now, in this specific case, what we are going to do now is actually to rewrite things. So I'm going to let x of t, if we want to implement it in our case, to a beta of I. This is what we have been looking at. And my x of t plus delta t is now going to be replaced by my beta of I plus 1. These are the iterations which I'm dealing with. And my gradient, delta v, is going to be replaced by the gradient as a function of beta of I. And when I do that, then I can actually use that equation, and I can set up a gradient descent scheme, which now keeps track of the previous values. So I would then define also a delta of beta of I plus 1, which is simply beta I plus 1 minus beta of I. And then I also have a delta beta value. So if I do that, then I get the following. I get a beta of I plus 1 is equal to a beta of I minus a gamma of I. And then I have my gradient. At the moment, not that one. I have my gradient, g of beta of I. And this contains a new parameter, which I call delta, which is just beta of I minus the previous value, beta of I minus 1. And what we would have then is an algorithm which runs as follows. So the algorithm so we would require the following things. You require a learning rate, gamma, and momentum parameter or memory parameter, and this parameter gamma, no, sorry, delta. Learning. Yeah, you require that one. And then the next thing you would require when you set up this algorithm is a initial value for beta, initial beta value. And we are going to use an intermediate parameter v and v of I. So let's set up these parameters, because the algorithm is going to be split in two steps. So I have a v of I, which is given by my previous value, beta of I minus beta of I minus 1, minus this gamma times g of beta of I. And that means that my new value, beta of I plus 1, is going to be given by the value which I have currently plus V of I. So this is just the equations which I'm going to implement. So I need then an initial values for these parameters, beta of I and V of I. Then when we want to set up the algorithm and want to run the calculations, we would have a while stopping criterion not met. And then I would, first thing, I would compute gradients. Compute the gradient. That will be the first step, which I do then. And then I compute this update, which is normally called the velocity update. So this V, since it's coupled to this Newton's way of thinking, where you have a velocity-dependent term, which appears in a differential equation. So you don't have only the acceleration, but you have the velocity times the friction term, because you're assuming that the friction is linear in the velocity. That's one assumption, which is pretty common in mechanics. So when we done that, the next step is compute this velocity term. So we compute this V of I equal to delta of beta of I minus beta of I minus 1 minus this gamma multiplied with a gradient. And I just put a gradient calculated at the value of beta of I. So I put an in subscript I here. And then the next step, then it's update B of I. So we get B of I plus 1 is equal to B of I plus this V of I. And this ends the while loop. Okay, that's pretty easy to implement. So this will be one of the things, one of the many variations which you will be dealing with in project number 2, in the beginning of project number 2. So you can run gradient descent with momentum, which is pretty common, but then we can actually improve it by including information about the gradients in this parameter gamma. And the next method is something which is called adaptive gradient or ADA-graph. But let's take a look at what this momentum can give us before we move into adaptive gradient, which is another way of setting it up. So let's go back to the Jupyter notebook. So what you will find here is an example of using gradient descent with momentum. So in this specific case, and you see now, I try to keep these functions as simple as possible. So this just, the function is x squared, not very fancy. And then we know that the derivative is 2 times x. I hope you don't get offended by these simple examples. So then I have a function here, which is a gradient descent algorithm. And what I do now, I perform these iterations. I calculate the gradient. I take this step and I evaluate this point, as you said. I do the solution minus step size times gradient. So my step size is my gamma. And then I append that one to the solution so that my solution then becomes equal to, so this is a standard, what you see here is a standard gradient descent. What you have here, just another way of writing it. And what I'm doing now, if you look at the solutions here, this is a plain gradient descent. These are the function values. And you see now that the plain gradient descent, after something like 30 iterations, it has put my gradient to 0. And you will see something like this. So it's slowly moving down to the optimal point. So we know that we have the minimum at x equal to 0. So x squared has a minimum at x equal to 0. Then we can do that with momentum. And in that specific case, I calculate the gradient again. I have this new change. I have the step size times the gradient plus this momentum times the change. So the new change, this value, which we called the V of I, is now given by the value which I have, and multiplied, and then I have the gradient multiplied by the step size. And then my new value is now given by this new change, and we have solution is equal to solution minus this new change, as we put up in the code there. If I now run this code, you will see that the same function, after roughly 13, 14 iterations, I have a gradient which now has approximated 0. And you see now that basically this is, that takes as an argument x equal to 0. And you see also that the number of iterations when I'm plotting them here is smaller than the one I needed with a plain gradient descent. So momentum gradient descent is something which we normally recommend that you include in your calculations. Okay? So that normally improves the convergence rate. So it's so simple to use that not using it is it's almost stupid, right? It's very easy to implement. So what you can do then is that you actually, in case the different iterations vary a lot, then you're smoothing out this variation by bringing in information from previous results, the previous values. So the next topic which we are going to deal with is actually stochastic gradient descent. And this is something which I thought we could actually start with next week. So I will defer this topic here till next week, because it may not be the best thing to actually bring in too many new elements. So the slides which you see here are slides which will be repeated next week as well. We will not work on the exercises on this topic next week, but it will come as an exercise the week thereafter when we begin with project number 2. So all the material now is a little bit out of sync with the project work. So that's why I want to bring it up, not next week, but the week thereafter, when we begin with a new project. So next week, I'm going to discuss stochastic gradient descent, and then we are going to implement this adaptive gradient. We're going to implement root mean square propagation and also ADAM. And then after we've done that, we are going to start scratching the surface of neural networks, which will be the topic for the second project. And then we need to be able to evaluate gradients. So I instead of starting with a new topic, I thought we could stop here if that's fine with everybody. Okay, guys. Have a good one and see you next week. Take care.